Hello. In this video, we're going to study the difference between rational functions and, well, functions that maybe used to be rational. Let's take a look. We have y equals x plus 2. That seems like a pretty simple graph. If we do this in red, we're going to have y-intercept over at 2, slope of 1, so over 1, up 1, and we connect the dots. Boom. We have a line, no big deal. Now this looks like we'd have some wild graph. We would maybe need to find vertical asymptotes, horizontal asymptotes, all sorts of things. But you know what? I want to use some factoring or some synthetic for that top. So I'm going to first simplify this as x. Well, here, let's even do it with the synthetic. So we would have 1, 5, 6, and negative 3. So 1, negative 3, 2, negative 6, 0. So y would equal quotient, so 1x plus 2, plus remainder over divisor. And because the remainder is 0, we just have x plus 2. Oh, well, that looks like we'd have the exact same graph. It looks like it's exactly the same. And it is, but it isn't. So the good news is that when we put it in standard form or simplified form, all this crazy stuff went away and we just ended up with the same graph. But this little term here, or the fact that we had an x plus 3 over here, it should make you pause and say, okay, well, I mean, they seem pretty similar, but I mean, look at them. They're not exactly the same. Maybe you could think of it like this. When we had this 0 over x plus 3 and we dropped that, we should probably make a statement like x could not equal negative 3, or maybe say we have an NPV, x equals 3, right? We would have said, you know, you can't plug in negative 3. It's not a value on the graph. And so when comparing these two graphs, the red graph is definitely a line, and the blue graph is definitely a line, but it's a line with an NPV. Let's see where that NPV is. When x is equal to negative 3, okay, y would be equal to negative 3 plus 2, which is equal to 1. So over here at negative 3, 1, 2, 3, 1, 2, 3, we're going to have a point at negative 1. Okay, so right here at negative 3, negative 1, this is our NPV. And we don't really want to put it as an actual point on the graph. We want to say that this is not a point on the graph. So we're going to erase it here. I'm going to actually erase the red graph too, just so we can look at it. And this is going to be an open circle. The way we represent an NPV on the graph is we put an open circle, or a hole, and then we continue on with the rest of the graph. So forgetting again about the red graph here, and just looking at the blue graph is a line, but it's a line with a hole in it, a line with an NPV. So the difference between these two graphs is that while the red graph is fully connected all the way through, the blue graph has this chunk, this little hole, this chomp taken out of it. And you would graph the blue graph the same as you would graph the red graph. You would graph this line, but then you would have to go and locate where that hole is, and you have to erase it and put that on, because that is an important feature of the graph. So let's look here. We have the graph y equals 2x squared plus 9x plus 4, and we would like to graph the function. Now, it probably simplifies, I'm telling you right now, probably has some kind of nice simplification, maybe even becomes a line again. But because of that x plus 4 in the bottom, we know there's going to be an NPV. There's going to be this extra feature, this hole. So at x equals negative 4, we're going to have some kind of hole. And to find the hole, you have to first simplify the graph. You have to draw it, but then you have to go back and erase that little section. So go ahead and pause the video and give it a try. Okay, so whether you do synthetic or you do factoring, just to change it up, I'm going to do a little bit of factoring here for us. Good practice. So this is going to factor, we could do group factoring. So we're looking for two numbers that multiply to give 8, because the two 2 times 4 is 8, and add to give 9. So I'm thinking maybe 1 and 8. So we get 2x squared plus x plus 8x plus 4. Factor the x and you get 2x plus 1. Factor the 4 and you get 2x plus 1. Then factor the 2x plus 1 and you get x plus 4. So if that was the numerator, we would now have 2x plus 1 over x plus 4 divided by x plus 4. Cancel it out, and you get y equals 2x plus 1. Okay, well that's easy enough to graph. We go up 1. There's going to be our y-intercept. And we know it's going to be over 1 and up 2. Okay. There's our graph. But of course, we have to have that whole. So when x is equal to negative 4, y is equal to 2 times negative 4 plus 1. That will be equal to negative 7. So we have to go back and add this whole here. Now, whether you do it exactly or you kind of eyeball it, as long as you label it, we should be okay. So I'm going to think it's kind of over here. This point is, this location of our whole is negative 4, negative 7. And then we just continue on with the rest of our graph. So the graph, again, is a line, but it's a line with an extra feature. It has a hole. Another word for it is a point of discontinuity. So the fancy word here for this is a point of discontinuity, sometimes abbreviated POD, but I like to just call it a hole because that's how you draw it on the graph. You put an open circle. Now for a little bit of extra stuff, let's do the domain and range. So the domain is every number except for negative 4. The way we write that is negative infinity to negative 4, union negative 4 to infinity. And the range is every number except negative 7. Negative infinity to negative 7, union negative 7 to infinity. All right, so go ahead and pause the video and give this graph a try. And then when you're done it, make sure you put the domain and range as well. Okay, so I'm going to try this one again with synthetic. It's nice to just try different techniques. 1, negative 3, 4, negative 12, and we're going to put the 3 over here. So this gives us 0 remainder. So y equals x squared plus 4. Oh, well, that's kind of cool. That's going to be a parabola. Parabola up with a vertex at 4. Over 1, up 1. So over 1, up 1. There's our parabola. So this graph is actually a parabola. But of course, we have an NPV at x equals 3. So when x is equal to 3, y is equal to 3 squared plus 4. So 9 plus 4, 13. So over at 3, we're going to have to go back and now erase. We have a hole here at 3 and 13. And just so it looks a little nicer, we might want to extend the arrow a little bit here. So there's our hole and the rest of the graph. Now, just a couple things to note here. I wrote NPV x equals 3. So you have to be careful here how you state this. So you either say x not equal to 3, because you say x is not allowed to be 3, or you could say the NPV is x equals 3, because NPV means non-permissible value. So the value that's not permissible is 3. If you said the NPV is x not equal to 3, in English you would be saying the non-permissible value is x not equal to 3, but that's a double negative. So then you're saying x can be 3. So just be careful here. If you write the NPV, you've already said not, so you don't have to put another not equals. It just doesn't really make sense in English. All right, anyways, that aside, let's go ahead and get the domain and range. So the domain is all the real numbers except for 3. So minus infinity to 3, union 3 to infinity. But the range is a little tricky. It starts out at a low value of 4. And you might be tempted to say it never equals 13. But just because it doesn't get to 13 on this side, if you look on the other side of the graph, it does get to 13. So while this side has a hole, this side doesn't. And so it definitely hits the value of 13. It hits all the values. So the range is actually 4 to infinity. A little tricky there. Okay, go ahead and pause the video and give this one a try. See if you can find the graph and then also state the domain and range. All right, assuming you gave it a try, I'm going to do, again, a factoring approach for the top. So I'm going to factor out a 2, then two numbers that multiply to 8. That'll be x plus 2, x plus 4. Those add to 6. So y is equal to 2, x plus 2, x plus 4, divided by x plus 2, x plus 4. Those cancel, and y equals 2. And of course, x cannot equal to negative 2, x cannot equal to negative 4. So those are going to be our two NPVs. We'll have to add those in a minute. But right now, I mean, this graph looks pretty cool. This graph is just simply the line at 2. So it's just a nice horizontal line at y equals 2. And then all we have to do is pop back over here at negative 2 and at negative 4. And we'll just take a little chomp out right here. Boom, boom. So we're going to put a couple holes there at negative 2 and negative 4. All right, there's our graph. Now for the domain, negative infinity, we can't have 4. So we got to put a negative 4 union. Then we can't have negative 2. We got to put a negative 2 union. And then we continue on from negative 2 to infinity. Again, you can think about the graph having like 3 sections. There's the left section, the middle section, and the right section. It's almost like a pair of glasses, right? Here's the one side, the one lens, the middle frame, the other lens, and the other side. So the graph comes in 3 pieces. That's why we have 3 pieces for the domain. Now for the range, the graph only ever gets to one value. It's kind of like the lowest it goes is 2 and the highest it goes is 2, so it's just 2. If you wanted a maybe more technical way of writing it would actually be with those squiggly brackets. You would just say the value 2. But I like writing it like this. It's just square brackets, 2 to 2. Okay, for this last one, you can go ahead and skip the domain and range, but I do want you to come up with the graph. Okay, this one is particularly challenging because nothing is factored. So we're going to start with that top, factor out the 2, and then on the bottom, ooh, that looks kind of messy. Yeah, let's just work on the top there. Let's just work on just the top. So the top is going to be x minus 3, x plus 2. Okay, now for the bottom, we'll need to do some synthetic. And this is where you can use a little bit of your sort of student brain. We're hoping something cancels with the top and the bottom. And because these are 2 factors on the top, it's not a bad idea to try one of these as a factor in the bottom. You don't have any reason to try it in the sense of, I mean, you sort of have to try anything for synthetic, but thinking like a student, you're like, well, I'm in math class and the teacher's been having stuff cancel, so maybe something cancels. Let's try one of these. So we'll put 3 here. That's going to be negative 2, negative 6, negative 8, negative 24. Oh, what do you know? It definitely worked. So we'd have x minus 3, x squared minus 2x minus 8. Then we do a little more factoring. This would be x minus 6, x plus 4, no, x minus 4x plus 2. Yeah, that looks good. Okay, so our final equation is y equals 2x minus 3, x plus 2, divided by x minus 3, x minus 4, and x plus 2. So like I said, this one cancels, and we're just left with 2 over x minus 4. Of course, with the restriction, x cannot be 3, and x cannot be negative 2. Now, this simplified version that we have is still not very simple. It's actually a rational function from a previous lesson. So this is going to be a graph with asymptotes and holes. My goodness. Well, let's go ahead and grab that asymptote. 1, 2, 3, 4. There's our vertical asymptote. Thankfully, the horizontal asymptote is at 0, so we can just put that right here. We're going to pick a point on either side of the asymptote. So if I plug in x equals 5, 2 over 5 minus 1 is 2. If I plug in 3, 2 over 3 minus 4 is going to be negative 2. Then I go ahead and add my swooshes. And I'm good to go. Well, not fully good to go because I now have to go back and chomp my holes. So at 3, there's going to be a hole. So actually this point I used is not even a point, it's a hole. That's okay. I'll label it negative 3 and negative 2. There's one hole. And then there's another hole at negative 2, so maybe I should extend my graph this way here a little bit. Let's go ahead and extend this all the way this way. Then erase it right here. Put a hole there. Let's get the coordinates. If x is equal to negative 2, y is equal to 2 over negative 2 minus 4. So that's going to be 2 over negative 6, negative a third. So this coordinate is at negative 2 and negative a third. So this graph here was all sorts of fun, because first we had to do factoring to see what canceled and get it in its simplified form. Then the simplified form was a swoosh graph, a rational graph, so we had to grab our vertical asymptote, and because there's nothing out here, our horizontal asymptote. Then we had to graph it by picking a point on either side of the asymptote, and then we had to go back and erase any locations for the holes, and then add the y values for those holes. So all sorts of skills going on here, but when you get the graph in the end, you should feel pretty satisfied and say to yourself, wow, I've combined all sorts of skills, right? Factoring, synthetic, canceling, asymptotes, plugging stuff in, all sorts of pre-cal skills are coming together to help me sketch this wonderful graph. Let's go ahead and take some notes on this. So here we are graphing holes. That's pretty much what we did today. And so when a factor cancels, you get a hole, also called a point of discontinuity. When a factor doesn't cancel, you get an asymptote. If you remember on that last example, we had an x minus 4 in the bottom that didn't cancel with anything, and so that gave us a vertical asymptote. If it's left over, and of course these two factors that I'm talking about, this factor and this factor, I'm talking about in the bottom of a rational function. Any factor in the bottom, if it cancels out with something in the top, right? If there's your factor and there's your factor, and they cancel out, you get a hole. But if it doesn't cancel out and you just have your factor left over, then you end up with a vertical asymptote. Okay, so for our example here, let's go the reverse. Let's create an equation for a line with a hole at x equals 2. So that's your challenge. You need to create an equation for a line with a hole at x equals 2. Pause the video and give it a try. Okay, there's lots of solutions for this, but if you want a line, maybe we could do y equals x plus 5. Any x plus something will do. And then if we want a hole at x equals 2, we have to have an x minus 2 on the bottom and an x minus 2 on the top. That will cancel. So this section right here creates the hole, and this section right here creates the line. And so this would be one solution. There would be multiple solutions, of course, right? Because all of your lines might be different. But this is the equation of a straight line that has a hole at x equals 2. Now for extra practice, you can try worksheet 7 and 7.5. I would probably add something to your notes here where you actually do a graph. So pick one and add a full graph here to your notes. And then any things to remember, it might be important to find the y value of a hole. You use the simplified equation. So you just take that NPV and you plug it into the simplified equation, and that will tell you the coordinates of the hole. All right, hopefully you enjoyed this video, and as always, thanks for watching.